I'll be talking about something of a slightly different flavor, and this talk might look a little more stylized and the problem might be a little more theoretical, but the goal is to see if there's some connections or if there's some way in which we can make this a little more realistic. All right, so I will be talking about cost shared networks. So, what do I mean by that? So, imagine that you have a bunch of agents on a network, and each agent wants to route traffic from some source to some destination node. Okay, so, every agent wants to select a routing path and connect and route traffic from its source to destination. Now, the kind of costs I would be concerned about in this talk are what I call fixed costs. Okay, so, what that means is that every edge that is used in any routing path has a fixed cost that has to be paid. So, how do the agents pay this cost? Again, I will look at the simplest scenario where all the agents using the edge simply divide the cost of the edge equally among themselves. Okay? So, that is what a cost shared network is. And of course, the goal, as in many problems that we have seen so far, is to minimize the overall cost. Okay, so, every edge has a cost, this cost is shared equally by all users of the edge, and I want to come up with routing paths such that the overall cost of routing is minimized. So, if given this question, this seems very familiar. This is in fact, if some of you know what the Steiner Forest problem is, this is exactly the same problem. You want to minimize the sum of costs of connecting a bunch of pairs, source destination pairs, a very well studied problem. People have known the answer to this for 15 years or even more, actually more than 20 years now. However, there is a slight twist. The twist is that the agents are strategic. Okay, what that means is that the agents have no interest in my setting of minimizing the overall cost of routing. All they care about is their own cost. So, remember, the overall cost is shared among the agents. So, what the agents individually care about is to minimize their individual cost without bothering about the overall cost that the routing is incurring. Okay. So, that is the setting I want to study. So, let us look at a couple of examples before we go further. So, let us say this is my network. I have two agents. One agent wants to send traffic from S1 to T1, the other agent wants to send traffic from S2 to T2, and the labels of the edges are the costs of these edges. So, let us say the two agents start off by using these two paths, the green and the red path. As you can see on the central edge, that is an edge of cost 2 that is shared equally among the two agents. Each agent pays a cost of 1. On every other edge, there is only a single agent, so the agent pays the entire cost of the edge. Okay, so, that is how cost is shared. Of course, the total cost of the routing is simply the edges used in the routing, which in this case is 8. Now, what you can notice in this picture is that the green agent, the agent who is sending traffic from S1 to T1, is in fact not happy with the state of the system. Why? Because the green agent can actually switch to a different path, and while she was paying a cost of 5 earlier, by switching she can reduce her own cost to 4.5. Okay, so, she will switch. But once the green agent switches, the red agent realizes that the path that is being used by her is not ideal either. So, the red agent might now switch to a different path as well. Okay. Earlier the red agent was using a path that had a cost of 3.5. Now, this is a path that costs less, it costs 2.5. Okay. So, what is happening is that the agents unilaterally are deviating to a different strategy or a different path, and once one agent deviates, that is triggering off a sequence or a cascade of deviations. So, if you look closely, it is pretty easy to see that this is a game, okay, maybe just a game. And as in all games, there are equilibria. Okay, so, in this case, what is an equilibrium state? A state where no agent wants to unilaterally deviate to a different path from the one that she is currently using. Okay. So, an equilibrium state is one where there is no less expensive route compared to the current route for every agent individually. Now, the first question you might ask is, do equilibria states even exist in these games? Okay. So, there are many games in which there may not be what is called a pure Nash equilibrium. So, there may not be an equilibrium where every agent chooses a single routing path. That is not the case here. In fact, here, as we will see very soon, an equilibrium, at least one equilibrium state always exists. Okay. There is at least one state where every agent chooses a single path and is happy with it in the current state of affairs, can't unilaterally deviate and improve their own situation. Okay. So, we will see this soon, but what this talk will mostly focus about is to look at these equilibrium states and try to understand how suboptimal these states are. Of course, these equilibrium states are being reached with a different goal from the overall optimum. Right. These equilibrium states are ones where the agents are individually optimum in a sort of local sense. So, for all you know, these equilibrium states can be extremely suboptimal from a global standpoint, and that is what we want to understand. How suboptimal can they be, and if they are really suboptimal, then what can we do to improve the situation? In particular, what kind of limited minimal control can a central controller have which would in fact improve the routing behavior significantly, or the routing would reduce the routing costs a lot. Okay. So, these are the two questions that I will focus on in this talk. So, let us try to address the first question. Unfortunately, there can be extremely bad equilibria in this setting. So, consider the following situation. There are n agents sitting at S who want to send traffic to T. There are two options. There is an edge of cost n, and there is another edge of cost slightly more than 1. Now, the problem is, if all the agents are residing on the expensive edge, if all the agents are currently using the expensive edge, the edge of cost n, then no one of them has incentive to deviate to the cheaper edge, right, because individually they are paying only a cost of 1, because n is shared among n agents, the total cost of n is shared among n agents, and none of them will deviate. But the problem is, if the best solution of course is for all of them to use the cheap edge. So, this solution, the solution that is at equilibrium, is in fact a factor n away from the best solution, best routing solution that you can come up in this graph. Okay. So, the cost of selfishness here, usually called the price of anarchy, is about n. Okay. So, again in this kind of a situation, we want to analyze what role the controller can play. In particular, let us think of a slightly different situation where the agents are still autonomous and can choose what they want to do, except that the controller can prescribe a particular routing behavior and suggest it to the agents. So, the controller decides what every agent's route is. The agent can look at that route and either say that, okay, I am happy with this route, I am taking it, or deviate to a different route. Okay. So, that is the controller has sort of minimal control in this situation. It can suggest routes, it can't force the agent to pick to choose the route. Now, this is, if you think about it, this is trying to study, the new situation is trying to study the best equilibrium in this setting versus the worst equilibrium which was being studied in the previous slide. Okay. So, the previous slide was really the worst case scenario. Here I am still looking at an equilibrium state, but I am trying to see what is the best equilibrium state, what is the best suggestion that the controller can make. Okay. And this is usually called the price of stability as against price of anarchy. Okay. So, in trying to understand what happens if the controller actually can choose the routing paths, but still needs to satisfy the agent's selfishness, we first observe that this is in fact what is called a potential game. Okay. And I will show what that means in the next slide. But one of the corollaries of this being a potential game is what I stated earlier, that there is always a pure equilibrium. Okay. There is always an equilibrium state where every agent chooses a routing path and is happy with the current state of affairs. So, what is a potential game and how does it apply here? Let us look at it. So, imagine that edge E is used by n sub E agents. Okay. Then we define the potential, which is just a function of edge E, as the cost of the edge times the harmonic number of the harmonic function of n sub E. Okay. It is the sum of these reciprocals till n sub E. So, that is what I define as the potential function of edge E, and the overall potential of a particular state is just the sum of potentials of the individual edges that are being used in the routing. So, now let us look at a very simple case where I have a bunch of n1 agents using an edge C1 and n2 agents using a different edge C2 to route between 2 points. Now, suppose an agent moves from the top edge to the bottom edge. What is going on is that on the bottom edge, what is the change in potential? On the top edge, the potential decreases by C1 over N1, because the last term in that harmonic sum goes away. One agent has left the system, has left the top edge. Simultaneously, what happens on the bottom edge is that one additional term gets added at the end of this potential expression. Okay. In this case, this additional term is C2 over N2 plus 1. Okay. So, the difference in potential after this move is in fact C2 over N2 plus 1 minus C1 over N1. Now, the interesting thing is that this is exactly the change in the shared cost of the agent who moved. The agent was paying C1 over N1 in the previous setting when he was on the top edge. When he moved, he is now paying C2 over N2 plus 1. So, in particular, if this move is performed by the agent, if the agent prefers to go to the bottom edge, it must be the case that this potential, the change in potential is negative. The agent actually decreases the shared cost that he is paying. And this argument generalizes. This is a toy example, but this is true in general. When an agent moves from one path to another, the change in potential is exactly the difference in shared cost, the selfish cost that the agent is trying to optimize, which means that whenever an agent makes an improving move, a move that decreases her selfish cost, it must be the case that the overall potential of the game decreases. Okay. So, these kinds of games are called potential games, where there is some global function which keeps decreasing as the game progresses. Now, of course, what this means is that there has to be an equilibrium, because if I just let the game run, the potential keeps decreasing. The potential can't drop below 0. At some point, it has to stabilize, and at that point, I have an equilibrium. Okay. So, that is one implication of this observation. Another implication is the following. Let me take my optimal solution, whatever is the best global routing, and let the game run from that point. Okay. I know that the game will terminate, let us say, and it will terminate, it has to terminate at an equilibrium state, otherwise the game keeps running, someone is not happy. Now, I know that over all these stages, the potential has decreased, potential can't increase at any point, which means that the phi, the potential at the equilibrium state, is upper bounded by the potential in the optimal state. But I know that the potential is at least the total cost of the edges being used, right. The first term itself is the cost. So, the potential is at least the cost, and at most the cost times harmonic of n, okay, which means that the final expression tells us that the total cost at equilibrium is at most the total cost at optimum times the harmonic of n, okay, which means that this ratio, the price of stability for these games, is no worse than log n, which is about the same as harmonic n. So, there is a sharp contrast between the worst case equilibrium and the best case equilibrium in these games. The worst case equilibrium, we said, has a ratio of about n. The best equilibrium has a ratio of log n or better. Okay, so, there is an exponential contrast. Now, the first open question, and this has been open for many years now, is can this ratio be improved? The best lower bounds that we know, the best that are really small constants like 2 or 3. We do not know any game of this form where the routing behavior, the best equilibrium, is off by a factor of 2 or 3 more than the optimum solution. Okay. On the other hand, the best proof that we have is slightly better than what I showed you. It's log n over log n. Okay. Can you bridge this gap? This has been a major open question in this domain. So, there has been essentially no progress on this question. So, what people have looked at are various special cases, and I want to mention one special case. So, one special case are what are known as broadcast games. So, what are broadcast games? There are two special properties that I assume. First, that every vertex in the graph, every vertex has an agent on it. Okay? So, there are no vertices that are empty, that do not have an agent. That is the first property. And the second property is that all these agents are trying to route traffic to a single gateway destination. So, there is a single node, a gateway node, that everyone is trying to route to. Okay. With these two assumptions, a lot more is known. In particular, there has been a series of works. So, from log n, it initially went down to log n, then log n, and then to a constant. But without going into all these results, let me say a little bit about why this is a much easier situation to handle. Okay. So, imagine that I have a vertex v that is routing traffic to the gateway node using an edge E sub v. Now, the interesting thing is that I can tie this edge E sub v to vertex v itself. Okay. It is impossible that vertex v, if vertex v stays in the game, it will continue to use E sub v. And if vertex v starts using a different path, then E sub v leaves the game. Okay. So, I can assign the responsibility of this edge, the cost of this edge E sub v, to vertex v. And once I have done these assignments, every vertex now is responsible for an edge. Now, one can show some sort of relatively standard primal dual arguments. One can show that if you have two edges that have about the same cost, some cost 2 to k, then the distance between those two corresponding vertices has to be large. Okay. So, all the vertices that are paying a large cost for their edges are well separated, and therefore, the total cost is not very large. Okay. So, this I do not want to go into the details of this. Of course, this basic argument gives you only a factor of log n, and then you need to refine it, and all these papers do that. But this is the reason, the basic reason why it is a much simpler situation to analyze is that edges can be charged to vertices which can pay for them. Okay. Now, what happens in multicast? Okay. If I do not have this property that every vertex has an agent residing at it. So, the problem is that suppose I have a structure like that, a routing structure where these two vertices u and v are both using edge E, but the vertex in the middle, the vertex where these two paths join, does not have an agent there. So, I cannot assign the cost of that edge E to this vertex, because that vertex does not have an agent. I can only assign costs to agents. And the problem, what I could do is I assign the cost of edge E to one of these two vertices using it, either u or v, or in some shared way u and v. Problem with doing that is that these agents are moving over time. So, suppose I assign the cost of E to vertex u. Now, what happens if u moves away, finds a cheaper path and goes to a different path? In that case, E must be assigned to v, and this transfer of assignment is something that we have not been able to figure out in more than 15 years now. So, we do not know any mechanism for being able to transfer responsibility. I want to briefly mention that we have made some very recent progress on this question. So, we have shown that we can go a little beyond broadcast games in showing a better price of stability than log n. In particular, we have shown that if you have a multicast game, but on what is called a quasi-bipartite graph. So, in a broadcast game, you only allow edges between agents. So, the blue edges in that picture. In these multicast games, you also allow edges between the blue vertices, the agents, and the non-agents. The kind of edges you assume you do not have in your graph are between non-agents. Okay. So, that is why it is still a special case, it is not the full general problem. In this case, we are able to show that the price of stability remains a constant, although you still have the same problem. you still have these non-agents residing in the network, and there are edges incident on the non-agents that cannot be charged to the non-agents. Okay. So, I do not want to go into details of this. Let me quickly say a few words about a couple of other questions in this domain that have remained open in spite of significant effort. One question that immediately springs to mind is, well, I have shown you that there is a good equilibrium, there is a bad equilibrium. Can I come up with these equilibria? The original motivation, of course, was that there is some controller who is suggesting these routing paths. Problem is that we have all these algorithms that achieve these equilibria are exponential time algorithms. In fact, there is no known polynomial time algorithm to find any equilibrium, good or bad. Okay? I give you a graph, you can't, we do not know any way of finding a stable spanning tree in this graph in polynomial time. Okay, so, this is an open question, and I think a very nice open question. Let me now, in the last 3 or 4 minutes, let me talk a little bit about the dynamics of these games. So, till now I have been assuming that there is a fixed set of agents who are sending traffic in the network. What if this set of agents changes over time? So, there are agents who join the network, there are agents who leave the network. How does the game behave in that case? Okay, so, here is an example. I have this graph, maybe there is only one agent to start with, trying to send traffic from S1 to T1. The cheapest path to do that is this path that I have shown. Now, second agent joins. When the second agent joins, she also chooses her cheapest path, which is again the green path that I have shown. But now what happens is interesting. So, what happens is that since the green agent has now used this central edge, now the first agent realizes that she can change her routing path and improve her cost. Okay. So, the red path can now change to this different path, and that path has a smaller routing cost than she was paying earlier. Okay. So, people joining or leaving the system can affect the stability of the system. At equilibrium state, if I leave the system or if I join the system, I can break the equilibrium, and then it will take some time to get back to equilibrium. So, the question is, what if I have these arrivals and moves? Okay. So, agents can arrive at any time, they can move between from their current state away to a better route at any point of time. How good is the equilibrium that I get at the end? And this is also open, nothing is known, except in a very special case. So, there is a paper by Charikar and others which shows that if I have all my arrivals to start with, so all the agents join the system, then nobody is allowed to leave. After they have joined the system using their best paths, now they are allowed to move. If these two sets of actions are batched, then you can in fact show that the ratio of the equilibrium to the optimal solution is not too bad, it is polylogarithmic. Okay. But in the general case, we do not know. What we do know in some very recent work with Shuchi Chawla, Safi Naur, Mohit Singh, and Siun Ambo, we have been able to show that if departures are allowed, so if people can join and leave the network, then in fact the situation is pretty bad. Then the equilibrium, you can get into situations where the equilibrium you reach is a polynomial factor away from the optimal solution. Okay, so, again the question is, what can I do if I have a controller which can impose some degree of control over how the system behaves? Now, again here the answer is that you can do quite a lot actually. In fact, if the controller only suggests moves, so all the controller does is at every point of time, if the system is not in equilibrium, it can ask an agent to go to a different routing path, which is a better path for the agent. So, the agent has incentive to move. So, if the controller is only allowed this ability to just choose a better routing path for agents, then in fact suddenly the equilibrium becomes much better, and you can get to within a logarithmic factor of the optimal solution. So, the crux of the story is that in both of these situations, whether you have a static set of agents or a dynamic set of agents, if the controller can even suggest routing paths, the overall cost, fixed cost of routing can be decreased significantly compared to a situation where the agents behave completely arbitrarily or completely autonomously and can choose their own paths. So, I do not have time to go into details of how this works. I will just skip this and I go to the summary. So, what I showed you was that equilibrium network games in general can be highly inefficient. So, while we know that things like spanning trees and so on are extremely easy to compute in a centralized fashion, the moment there are strategic agents at play, these problems become extremely hard, and it can lead to very bad solutions. And these problems become hard in two respects. One, it can lead to bad solutions that are not desirable. The second is that we do not know any way of computing any stable solution, even for the simplest problem in this domain, which is spanning trees. And then towards the end, I looked at this issue of agents joining and leaving the network, a more dynamic setting. And in this dynamic setting, we again saw a similar kind of behavior. If I have no control over the agents, then the inefficiency is pretty large. If I have a little bit of control over the routing, then the inefficiency can be decreased significantly. Right? Thank you. Yeah.
It's a very nice talk. Do you have any sequence of moves which is exponential? You are trying to find an equilibrium in polynomial time, but do you have examples where, depending on if they chose the moves to move in certain arbitrary order, it may take them exponential time to get to a equilibrium?
There are sequences of moves that are exponential, but there are strategies which will get you to equilibrium solutions where there is no known exponential lower bound. So there are worst case strategies which will take exponential time to converge, but there are strategies that are possibly polynomial time. We just do not know that it is. Yeah.
Actually, I came a little late. Did you, in your original problem, you have SI-TI pairs?
So with SI-TI pairs, we are still stuck with that logarithmic bound that comes from potential analysis.
Okay. And is it easier to prove, and you still don't know whether finding an equilibrium is PPAD hard for that?
Yeah, it's not known. So for all of these problems, it's not known if finding an equilibrium is hard. The only thing that's known is if the graph is directed, then you can show that the potential analysis still works, but that's the best you can do. So for directed graphs, the best case equilibrium is no worse.
If the paths are short, if you require the paths be short, then is it easier to?
Depends on how short. So if it's constant length, then the new result that I presented on quasi-bipartite graphs, that can be extended to constant length paths. So quasi-bipartite gives you length 2 between any pair of terminals. It can be extended to constant length, but I do. Yeah.